Alright, so in a previous video we just had an introduction to a bunch of these properties. Now we're going to talk a little bit more about each one. So here's our change of base property. It's a really great rule to use to change the base of any logarithm to another base that might be easier to use for whatever reason frequently so that we can use our calculator. So we're going to do example 3 here. Before we do that, I want you to notice on this formula. So we have a logarithm with a base and an argument, right? We want to change the base. So notice in our formula, the base is changed to a different value, but the base on the top and the bottom is the same. The other numbers that were in our original logarithm, the argument, goes on the top logarithm in the numerator, and the former base goes as the argument on the logarithm in the denominator of our change of base formula. So one way I like to remember this is the argument is a little bit higher than the base because the base is subscript. So the argument is the one that goes on the top and the subscript base is the one that goes on the bottom, and then both of those will have a new base, generally base 10 or base E, not always, but in this case that's what we're going to do. We're going to change this to base E. So we start with our logarithm, base 4 of 5. We're going to change this to base E. Now remember, we talked about this just barely, that base E is written as ln instead of log with an E at the end. So ln means log base E, but we write it as ln and we call it natural log. Okay, so then base E is already indicated in what we've written. So now remember, the 5 is higher than the 4, so we're going to draw 5 in the numerator, and then natural log, so that's our base E, with 4, the base for the argument in the denominator. That is an exact way of writing that answer. Now usually the whole point of using a change of base formula is so that we can get an approximate value with the calculator. To do an approximate value, we're just going to type the natural log 5 divided by natural log 4. Now, if your calculator doesn't automatically close the parentheses after the 5 or put parentheses in there, make sure you do that. So your calculator should probably look like this when it's typed in. Natural log 5 divided by natural log 4 with that argument in parentheses. And that will give you an approximate answer. I rounded mine, so I got 1.16. All right, let's think of another way we could verify this answer. What does logarithm notation literally mean? Well, log base 4 of 5 literally means 4 to what power is 5? So I think that the power is 1.16 because that's the value my calculator just gave me when I solved this problem. Well, we can check that another way using an exponent. We can actually take a calculator and use the little caret button and type in 1.16 for our power and hit enter. When I did that, my calculator gave me 4.9933 blah 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 blah, which is approximately equal to 5, right? So, using our answer as a power, verified that the answer is correct according to what a logarithm means. We used the change of base formula, we got an answer using a calculator, then we used that as a power to verify that that really is the power on 4 that gives us a value of 5. Hopefully you're starting to make all those connections between logarithms and exponents and what everything means. Okay, then we have inverse properties. This first one's a little weird, but the whole idea is that exponentials and logarithms are inverses of each other. So if you have an exponential and a logarithm with the same base, they basically cancel each other out. So b to the power of log base b of x is just going to be x, because the b and the logarithm, the exponential and the logarithm, cancel each other out. Same idea here. Log base b with b to the x power is just going to be x, because we have a logarithm base b and we have an exponential base b, and together those inverses cancel each other out and we're left with x. The 1 and 0 exponent properties we looked at earlier, and I said, well, let's kind of verify those, but hopefully these are pretty obvious. Since a logarithm of base b is the value of the exponent that gets that argument, isn't it true that base b to the first power should equal the argument b? And it does, right? That's why any logarithm with the same base and argument is a value of 1. Now that's really convenient when you see problems like that, because when they turn into 1, if it's multiplying times something else, it just goes away. Log base 3 of 3 is 1, or log base 10 of 10 is 1, and then we can just get rid of the logarithm out of the problem. This is the same idea. The base is b, the exponent is 0, and anything to the 0 power is 1. So the logarithm of 1 is always 0, no matter what the base is. This is also very convenient in getting rid of logarithms when we see this happen. Alright, now we're getting down to these nitty-gritty properties that we need to understand so that we can expand and write logarithms as single logarithms. Okay. This one's called the exponent property or the power property. When I explain this, I kind of like to think of this as, a logarithm is an exponent, right? So what if we have a problem like x to the third? And x to the third has an exponent. The exponent is a 3. Well, what if we take our x to the 3 to another power, x squared? So we now have x to the third squared, which literally means x to the third times x to the third. So we're duplicating that third power. We just multiply those numbers together, and that gives us an x to the 6th power, right? A power of a power multiplies the powers together. Well, if a logarithm already is an exponent, but then a logarithm has an exponent, then it's like we have an exponent with an exponent, and we can just multiply those exponents together. So the exponent m in this problem can actually move forward to the front of our logarithm and multiply as a coefficient instead, because powers of powers just multiply the powers together. So a power on a logarithm is a power of a power, and we can just multiply our powers together. Okay, so we can use that property in solving this problem right here. We can solve this a couple of different ways. Let's do this one way by just changing it to log form. So let's go ahead and change it to log form. So if we change this to log form, we have exponent base 2. So that would be log base 2. And then x is the exponent, so that would be our logarithm is the exponent, and then the argument is the other number, 3. So this is basically saying the log base 2 of 3 equals x. So we've just found the value of x, more or less. We found the exact value of x is log base 2 of 3. Now that doesn't really mean anything to us in that form, even if it is the exact value. If we want an actual numerical answer, then we could use like the change of base formula to find the answer in the calculator. So to use the change of base formula, let's go ahead and change this to log base 10. So that would be log base 10 of 3 over log base 10 of 2. Now we can put that in a calculator and get an approximate answer for it, which we don't really care about at this point, but we can. We could get that approximate answer, right? So there's another way we can go through this problem, though, by using the one-to-one property. And by doing that, we're going to be able to see this power property we just learned about. So another method is to use our one-to-one property. If you don't remember what that is, I like to fondly call it the golden rule of algebra. So do unto one side what you do to the other. So in this case, we have an exponential, but if we do a log on both sides, we have followed the golden rule and we've done the same thing to both sides of the equation. I chose a log base 10. Now I can use the power property, and that x can be rewritten as a coefficient or as a product of our logarithm and x, right? So all I've done is I've used the product property to change the power on a power as a product of two powers instead. That gives me the ability to now divide by everything and get x by itself, which gives me log 3 divided by this piece left over here, log 2, which I again could put in a calculator and get an approximate answer. Look at how I got the same exact answer I got when I used changing this to log form and then using a change of base formula. Either way, same answer, but this one used this property that we just learned about.